Hello, today's first lecture is on Introduction to Man-Made Fibers. So let us look at the things that are around us, and one would be surprised to know that most of them are polymers. So let us look into them. The products, devices, and components that we purchase and use are all made up of materials, and solids that we use may be subclassified as metal, ceramics, or polymers. So polymers may be natural or synthetic. Almost all textile fibers are polymers. Some examples of natural polymers are cotton, wool, silk, jute, etc., whereas polyester, polyamides, polyolefins, etc., are examples of synthetic polymers that can be converted into fibers. So there are some non-polymeric materials also which are man-made, and inorganic fibers such as carbon, glass, metallic, and ceramic fibers possess several advantageous properties. Like some of them may have excellent mechanical properties, some of them may have very high or very low electrical properties, thermal conductivities are higher, excellent heat and chemical resistance, maybe better in these non-polymeric fibers, and these properties are not offered by ordinary polymeric fibers. So, what are the factors that decide the properties of any particular fiber? Man-made fiber properties are determined by a variety of reasons, which are considered at three different levels. So, broadly subclassified, one can say that these properties depend on these three things. That is the chemical structure of the polymer itself, the fine structure, and the gross morphology. We shall see what this means one by one. So chemical structure means that the plastics are polymers which are derived from petroleum products, and most of these polymers are made up of carbon and hydrogen atoms. Polymers that contain hydrogen and carbon atoms are called hydrocarbons. So one can see in the image here they are classified as aliphatic and aromatic. So let us see what is meant by that. Carbon atoms can form four single bonds with four other atoms. If the carbon atoms in a polymer are bound to four other atoms, the polymer is referred to as a saturated hydrocarbon. So in the aliphatic type, one can see that each carbon atom is connected to three hydrogen and it has one bond with another carbon atom. So each carbon atom is fully saturated, and this type of a hydrocarbon is called as a saturated hydrocarbon. So now let us look at the other formulas in the image that is given over here. If on the other hand the carbon atom is not bound to four other atoms, it will typically form a double or a triple bond as shown in the other three cases, um, as needed with other carbon atoms. In this case, the polymer is referred to as a unsaturated hydrocarbon. This distinction is important as unsaturated polymers are generally unstable and are more reactive. So, if it is an unsaturated hydrocarbon, one will usually find that they are generally unstable and they are more reactive also. So, it's better to know what kind of hydrocarbon we are dealing with. So, different types of polymers are produced when the hydrogen atoms are substituted for other atoms or molecules called functional groups. So, when we substitute hydrogen atoms with some group of molecules or functional groups, then the properties of that polymer changes. So, examples of functional groups are hydroxyl, carboxyl, amides, and aldehydes. So, the type of functional group attached to the hydrocarbon influences the property of the entire polymer. The chemical structure influences chemical reactivity, moisture absorption, dyeability, swelling properties, physical properties of the fiber. So, on the next level, now we look at what the fine structure is, what do we mean by that, and how it affects man made fibers or the fiber properties. A polymer, therefore, is a series of long chain molecules composed into a complex arrangement to make a solid. There are two possible arrangements of the molecular chains. They are either crystalline when they arrange themselves neatly to have a long range order, or they are amorphous and randomly packed with no discernible order. So, for the molecular chains within the polymer, one can have either crystalline regions where they are neatly arranged, or they may be amorphous. And normally, any polymer will contain both these regions, crystalline as well as amorphous. and therefore they are called as semi-crystalline. So as one can see in this diagram shown here, one molecular chain passes through many crystalline regions as well as amorphous regions. So in a fiber, this can happen. Um, while just to give a parallel example, one can imagine the molecular chains to be fibers, maybe within a sliver, and one can imagine that if the fiber is long enough, it can pass through various well arranged, neatly arranged regions, as well as completely randomly packed regions. While a polymer can be completely amorphous, it will never be completely crystalline, but instead will also have regions that are partially amorphous. These structures are therefore referred to as semi-crystalline. So, the degree of crystallinity may range from completely amorphous to up to 95% crystalline. Polymers with molecular chains that have a large irregularity with respect to attached functional groups find it difficult to arrange into an orderly fashion and therefore favor the formation of an amorphous structure. The fine structure, that is the molecular organization or arrangement of the molecules within the fiber, influences physical properties as well as chemical properties. So, at the primary level, the chemical structure of the molecular chain will decide the properties of the fiber. At a second level, the fine structure, that is how the molecular chains are arranged or organized, will decide the fiber properties. And at the next or the third level, it's the gross morphology, that is, gross morphology means fiber surface or the cross section or the features that are there on the surface which are larger than zero point 0.3 micrometer, which are observable by a normal optical microscope, will also influence certain properties. So if one, for example, if one simply changes the cross section of the polymer, if all the polymer is the same in all these cross sectional shapes, still there will be one will find that the properties change from one shape to the other. Just simply because we have changed the morphology of this polymer, the way it has been shaped, and one can see change in the properties in terms of, say, appearance, feel, and performance properties of fibers made by using such fibers. Some physical properties of the fibers also change because of this example, like cross-sectional shape changes. Or if one were to add certain features on the surface of the fiber, again one may see some changes. For example, this is a hollow fiber, or a triangular cross section fiber, or a kidney bean shaped, or maybe this square shaped with hollows inside. All these various shapes will affect certain physical properties also. So with this, we come to the end of this session, where we saw how man-made fibers are affected at three different levels. That is the chemical structure of the molecular chain, the arrangement of the molecular chain, as well as finally the morphological changes, that is the shape, etc., or the surface of the fiber may bring about a change in the properties of the final man-made fiber. So with this, we end the session today. Thank you.